teasing out a fascinating story from a 375 million year old speck of light. I'm Tonya Hall, and joining me is Dr. Thomas Holoien, Carnegie Fellow at Carnegie Observatories in Pasadena, California. Welcome, Tom.
Hi, it's great to be here.
So, in what do you specialize at Carnegie Observatories?
So I am a postdoctoral researcher, and I work primarily with a survey project called the All-Sky Automated Survey for Supernovae, or ASSASSIN. Basically, we are scanning the sky every night with small robotic telescopes, and we're looking for things that are changing. So for me particularly, I like to specialize in things associated with stars that are dying, such as supernovae, so stars that explode at the end of their lives, or more exotic things like stars getting shredded by black holes and things like that.
Well, speaking of which, last January, you were off minding your own business at Carnegie's Las Campanas Observatory when a once in a millennia tidal disruption event happened. It actually happened about 375 million years ago, but Earthlings were just now able to notice it. Tell us about what happened.
Yeah, so what happened was we detected one of these events. We call them tidal disruption events. It's when a star gets destroyed by a black hole. And what was happening, or what happened was I was observing down at Las Campanas Observatories in Chile. I was using some larger telescopes to get some follow-up data on some of the assassin discoveries we had made. And our telescopes in South Africa flagged this new object, something that was getting brighter in the sky that wasn't there before. So because I happened to be observing at the time, I turned our larger telescopes onto it, and we were able to confirm pretty quickly within less than a day that this was one of these tidal disruption events. And that's just in itself is very exciting because it typically takes us a little while to confirm these things. We're not always sitting on a telescope when they're discovered. So we were able to confirm it and start getting other data really quickly. And what was also really cool is that we knew that this was being monitored by one of NASA's satellites called Tess, which is a planet hunting satellite, excuse me. And that typically uses or gathers data in a different way. And so we knew this would be a really great data set once we got all the data together. So we wanted to observe it as much as we could, and it ended up being a really great collaborative effort between all these different groups.
In fact, you mentioned Tess. Dr. Sarah Seeger, the Deputy Director of Science for NASA's Tess mission, was a recent guest. What did Tess contribute to the finding?
Yeah, so what TESS typically does is it's looking for planets that are transiting in front of a star. So you have a star and the planet goes in front of it, and that makes it get dimmer for a little while and then brighten again. And so to find these things, it stares at a large patch of the sky where there's a lot of stars, and it takes an image every 30 minutes trying to catch exactly when these things start to get fainter and then brighter. And what's nice is that in the background of all these stars are a lot of galaxies. And so what happened was this just happened to occur in an area that Tess had been monitoring for several months already and continued to monitor for several more months. And so we have basically every 30 minutes for an entire year, we have images of this part of the sky. So we were able to see exactly when this tidal disruption event started to get brighter and exactly how long it took to reach its brightest point. And that's really unique. We've never been able to do that before, to get that exact measurement. And that time is really useful because it helps us model some things that are going on with the black hole and the star and sort of the dynamics of all the gas that's being thrown around as this is happening.
What did we learn from these observations?
Yeah, so black holes are black. They're so compact, nothing can get out, not even light, right? So we know that they're important for a lot of things. In particular, they play a big role in galaxy evolution. Most galaxies have a supermassive black hole at the center, including the Milky Way. But we can't really study them directly, typically, because there's no light to look at. And so what we need to do is find ways to observe how they affect their environment. So in some cases, you have a lot of gas that's actively being eaten by the black hole, but typically this isn't happening. So when a star gets shredded like this, it briefly lights up this black hole because all this material that used to be a star is getting heated up to really high temperatures and it glows, and we're able to see that light. And so from that, we're able to learn things like how heavy and massive this black hole was, how long it took the gas to be absorbed and eaten, and how that was happening exactly, things like this, where these are still sort of new discoveries, so we're still learning a lot about them every time we find one. But hopefully, we're hoping that we can use them to sort of measure black hole populations, measure their masses, measure different properties of them, and learn more about how they could affect their galaxies and sort of how the universe evolves and on a bigger scale.
How long did the shredding and absorption take?
So the actual tearing apart of the star happens very quickly. This star is passing very close to the black hole, so it's moving really fast. Speeds kind of getting fairly close to the speed of light. So as it gets really close, it gets stretched out. What happens is the gravity on the front end versus the gravity on the back end of the star relative to the black hole, the difference is so strong that it stretches the star out into this long stream of material and just tears it apart. And so this happens very quickly. A lot of it gets thrown out. The rest of it tends to get flung around the black hole at really high speeds, and it's very chaotic. There's the gas is crashing into itself and blowing out, and more little mini explosions and things like this. So we think this tends to take something between like a year or maybe a couple years. But as I said, we've only found maybe 20, 30 of these before. So the time scales involved are still kind of unknown, but typically they take about a year, and this one is actually still ongoing as of today when we're talking.
So, what technologies allow us to view, measure, and understand what's happening beyond the limits of our own galaxy in such a small segment of the sky?
Yeah, I mean it's really great because a lot of different kinds of telescopes contributed to this research and in different ways. So, this ranges from Assassin, which actually uses very small robotic telescopes. These are 14 centimeters. They're smaller than what most, amateur astronomers would have in their backyard. These just scan the sky every night. That's what we use to discover it. But then to get more detailed observations, you have things like Tess in space that's observing it at high cadence every 30 minutes. We used another satellite called Swift from NASA that observes in ultraviolet and X-rays, which you can't do from Earth because the atmosphere blocks those wavelengths. So we need space telescopes for that. But then we also use telescopes down at Las Campanas Observatory and in other places on the ground that are much larger than the Assassin ones to get images in different wavelengths, to get different types of observations. And these can tell us all kinds of different things about how hot the material is, how fast it's evolving, what it's composed of, and things like this that just sort of it all comes together when you put the whole picture together. It's really great.
So, what benefits accrue to the general public from these types of discoveries?
Yeah, so with tidal disruption events in particular, as I said, we're trying to learn more eventually about black holes and what the sort of larger black hole population could look like, and how large galaxies like the Milky Way can form, and how these large black holes form in their centers. The creation of these really massive black holes is still kind of a mystery. We're not really sure how you get a billion times the mass of the sun into one little spot in the lifetime of the universe. So we're trying to figure out, sort of on a broader scale, how we got here, and learn more about some physics that can't really be probed in other places, that just doesn't happen anywhere else. But then more broadly, looking at all the different types of things that surveys like Assassin can find. Supernovae involve massive nuclear explosions, so we're learning about nuclear physics that could potentially be applied to power or other things here on Earth. We learn about how stars evolve over time, so that tells us kind of what will happen with our sun, a few billion years from now. So there are a lot of sort of real world applications that you could find based on all this different types of science that we're doing. So it goes beyond just a curiosity into the nature of the universe.
Dr. Thomas Holoien, Carnegie Fellow at Carnegie Observatories in Pasadena, California. Thanks again for joining us, Tom, and congratulations on this research and discovery. If somebody wants to connect with you, if maybe they want to find out more about the work that you do, how can they do that?
So I would suggest going to the Carnegie Observatories website. That's obs.carnegiescience.edu, obs.carnegiescience.edu. Also, you could check out the hashtag Black Hole Week on Twitter. NASA actually did a big press push for this and had a big event a few weeks ago, just all about black holes. So you can go on there and learn more about this and some other exciting black hole results from a few weeks ago.
Sounds good. Thanks again. And if you guys want to find more of my interviews, you can do that right here or go to tonyahall.net. Thanks for watching.